Hello everyone, today we will be covering the quantum mechanical model. In this video, we will be discussing the following topics. What is the quantum mechanical model? What is the principal quantum number? What is the azimuthal quantum number and its S, P, D, F notations? What is meant by the magnetic quantum number? And how is it related to the electron orbitals? What is the spin quantum number? And finally, the application of the quantum model and its numbers. Please make sure to subscribe and support the channel. Now, let's get started. The quantum mechanical model is the most accepted and accurate model for an atom's electron structure. According to modern quantum mechanics, the probability of finding electrons is highest in regions around the nucleus called orbitals. It is impossible to locate the exact location of an electron at a given point in time. This is also known as the Heisenberg's uncertainty principle. Instead, the quantum mechanical model provides 4 quantum numbers that holistically describes any electron in a given atom by specifying the orientation of its orbital. These numbers are as follows: principal quantum number, azimuthal quantum number, magnetic quantum number, and the spin quantum number. Firstly, the principal quantum number is represented by the letter n. This value corresponds to the energy and the distance of the electron from the nucleus, aka the radius of the electron shell. Basically, you can think of it as the energy level in which an electron is located around the atom's nucleus. Higher the n value, greater the energy, and larger the radius of the shell of interest. N is a positive integer number starting with 1. Therefore, n equals 1 is the innermost shell or the ground state. When an electron in a lower energy level absorbs photons, they get excited and move to a higher energy level. It's important to note that this does not mean that electrons travel in clearly defined orbits around the nucleus as Bohr postulated. This diagram simply provides a visual representation of the electron's motions. The second is the azimuthal quantum number. This is also known as the angular momentum quantum number and is denoted by the letter L. It corresponds to the number of subshells present in a principal quantum number and the shape of the subshell. As such, this quantum number provides important information about an atom's possible chemical bonding interactions and bond angles. As mentioned, the azimuthal quantum number describes the number of subshells present within a given principal number. In fact, the possible values for L ranges from 0 to n-1. Therefore, shell n equals 1 has only L equals 0 subshell. N equals 2 has 0 and 1 valued subshells. N equals 3 has 0, 1, 2 valued subshells. And n equals 4 has 0, 1, 2, and 3 valued subshells. As shown above, each subshell is defined by a unique L value, and this value is limited by the value of n. Secondly, the azimuthal quantum number also describes the shape of the subshell. Similar to how the principal quantum number is designated by a number, the azimuthal quantum number is denoted by a letter. This is known as spectroscopic notation. Therefore, the subshell with L equals 0 value is denoted by S, which is spherical in shape. The subshell with L equals 1 value is denoted by P, which is dumbbell-shaped. L equals 2 is denoted by the letter D, and L equals 3 is denoted by the letter F. The shapes of D and F subshells, i.e., the subshells with L values of 2 and 3, are too complicated to be defined by a shape. It is within these subshells that the orbitals in which the electrons can be found are located. In fact, the maximum number of electrons that can be held within a given subshell can be determined by the following formula: 4L plus 2. For example, the s subshell has a maximum of 2 electrons. P subshell has a maximum of 6 electrons. D subshell has 10 electrons, and F subshell has 14 electrons. The azimuthal quantum number can be more easily understood by the following periodic table diagram, where the spectroscopic notations are displayed. The energy of the subshells increase with increasing L value, similar to the N value. However, the energy of subshells from different principal energy levels may overlap, therefore may not always increase sequentially. The electron subshell flow diagram will be useful in remembering this pattern, and this will be discussed in another video. The third is the magnetic quantum number, aka ML. This number describes a specific orbital in which a given electron is most likely to be found in a subshell. This value ranges from negative L to positive L, including 0. The possible values for ML for a given subshell can be determined by the formula 2L plus 1. For example, the S subshell, i.e., the subshell with L equals 0 value, has one orbital with the ML value of 0. P subshell has 3 orbitals with the ML values of negative 1, 0, plus 1. D subshell has 5 orbitals with the ML values negative 2, negative 1, 0, plus 1, plus 2, and so on. Remember, one orbital can hold only 2 electrons. Therefore, the S subshell with one orbital will have a total number of 2 electrons. D subshell with 5 orbitals will have a total number of 10 electrons. Lastly, the spin quantum number is denoted by ms, and this describes the spin of the 2 electrons present in one orbital. An electron only has 2 spin orientations, plus half and negative half. This is because when 2 electrons are in the same orbital, they must oppose each other's spins. These electrons are said to be paired. On the other hand, 2 electrons with the same ms value in different orbitals will be considered to be parallel spin electrons. Now to summarize, let's describe the electron orbitals of the third principal energy level with all 4 quantum numbers. As you can see, the third principal energy level has 3 subshells with L values of 0, 1, and 2. In other words, the third principal energy level has S, P, and D subshells. The S subshell has only one orbital with the ML value of 0. P subshell has 3 orbitals with ML values of negative 1, 0, and plus 1. D subshell has 5 orbitals with ML values of negative 2, negative 1, 0, plus 1, and plus 2. As previously mentioned, each orbital has a maximum of 2 electrons with spins of positive half and negative half. To find the maximum electrons present in a given principal energy level, we can use the formula 2n squared. Therefore, the third principal energy level has a maximum of 18 electrons, as shown in this table. These quantum numbers, especially their spectroscopic notations, are used for electronic configurations. This will be covered in another video, so stay tuned. If you found the contents of this video to be helpful and would like to learn more, please make sure to subscribe to the channel. See you next time.